Good afternoon, everyone. I am Yashwant Demke, a student at Nitya Meenakshi Institute of Technology, and today I am here to talk about a subject that is incredibly important in today's world: sustainable engineering. This is more just an academic concept, it is a philosophy that guides how we think, design, and innovate. We live in a time when resources are limited, pollution is increasing, and climate change is a real threat. In this context, the role of an engineer is evolving. We are not just solving problems anymore. We are solving them responsibly, keeping in mind not just the present but also the future. Sustainable engineering is about integrating environmental and social economic considerations into every stage of design and implementation. It is a commitment to developing solutions that work long term for people, for the planet, and for the industries. Through this presentation, I will explore key aspects such as sustainable design principles, life cycle thinking, and sustainable tools, and more. So, sustainable engineering principles: efficiency in resource use, whether it's material, energy, or water. Our goal should always to be use resources in the most efficient way possible, reducing both costs and environmental impact. Use of renewable resources. Sustainable engineering emphasizes shifting from finite and non renewable resources like fossil fuels towards renewable alternatives like solar, wind, and biomass. Design for environment, DFE. This principle means designing products in a way that their entire life cycle has minimal environmental impact, including during production, usage, and disposal. Pollution prevention. It's always a better to prevent pollution than to treat it later. This principle encourages proactive thinking in system design to avoid emissions and contaminations at the source. System thinking. This involves understanding how all parts of a system are interconnected. An sound solution in one area shouldn't cause harm in another. Everything must work in a harmony. Long term vision. Sustainable design should consider not just the initial phase but the long term impact on future generations. These principles don't just belong in textbooks, they should be in the foundation of every design, every project, and every decision we make as engineers. At Nitya Meenakshi Institute of Technology, we are being trained to think holistically and apply these values in real world scenarios. So, next is life cycle thinking. Life cycle thinking, also known as LCT, is a transformative way of approaching engineering. Instead of thinking only about the end product, LCT encourages us to look at the entire journey of a product or system from beginning to end. So let me break down this. Raw material extraction. Where do the raw materials come from? Are they mined or grown or recycled? What are the environmental and social costs of extraction? So the next is manufacturing. What energy is consumed in manufacturing? What emissions are waste or generated? Can we reduce or reuse of any of these inputs? So distribution. How far does the product travel? What is the carbon footprint of transportation and packaging? Use phases. During its use, how energy intensive is the product? How long does it last? Can we upgrade it or repair it? End of life. What happens when the product is no longer useful? Can it be reused or recycled, or does it end up on a landfill? Thinking life cycle encourages us to shift from a linear systems, make us disposed to circular systems, make use cycle remake. It opens us opportunities to improve our every stage and create designs that are both high performing and environmentally sound. So, as a student as at NMIT, embracing the life cycle thinking will prepare us to build sustainable cities, machines, products, and systems that respect the full arc of impact. Sustainable design tools to translate sustainable ideas into practical outcomes. We rely on design tools. These tools help us evaluate the environmental impact of engineering decisions and choose better alternatives. So let's explore a few of them. LCA, Life Cycle Assessment. This is one of the most comprehensive tools. It quantifies the environmental impact across all stages and product lives, including the CO2 emissions, water usage, and toxicity and more. Carbon footprint calculators. These tools measure the total greenhouse gas emissions associated with the product of activity. These are essential. These are essential for the industries are aiming to meet carbon neutrality goals. Material flow analysis (MFA) helps track the flow of materials through a system to identify inefficiency and waste. Energy modeling software tools like Equest and Energy Plus help simulate energy usage in buildings, allowing architects and engineers to optimize efficiency before construction even begins. Design for disassembly. This approach ensures that products can be easily taken apart for the repair or recycling, reducing waste and extending usability. Greenhouse standards. Example LEED. These frameworks guide the sustainable design and construction of buildings. At our college, learning how to use these tools puts us ahead of the curve. It trains us to not only create but to optimize, making choices that are backed by data and triple bottom line. The triple bottom line TBL is a foundational concept in sustainable development. It argues that success isn't measured just by profit but by the impact on people, planet, and profit. Let's go deeper into each component. People, social sustainability. This involves ensuring human well-being. Are workers treated fairly? Does the community benefit from the project? And the products are safe for users. Social sustainability is about ethics, equality, and respect. Planet environmental sustainability. Does the project protect natural ecosystems? Are emissions and waste minimized? Does this use resources efficiently? So, profit. The economic sustainability. Sustainability must also be financially viable. A solution must generate or save enough value to sustain itself and encourage adoption. Take, for instance, green infrastructure like rain gardens or permeable pavements. These systems manage stormwater, planet, create jobs for people, and reduce maintenance cost, which is a profit. Make what makes TVL powerful in what prevents us from focusing on just outcome like cost of performing and forces us to consider a broader, more responsible impact. As engineers, we must always evaluate how work affects all three aspects. Engineering isn't just about solving problems; it is about solving the right problems in a right way. So, barriers to sustainable engineering. Even though sustainable engineering offers long term advantages, there are several barriers that slow down its adoption in both academic and industry. Initial cost and ROI concerns. Many sustainable technologies require high and upfront investment. For example, solar panels or green building materials may cost more in initial, even though they save money in a long term run. Short sighted budgeting can deter decision makers. Lack of awareness in some industries of rural regions, people simply don't know our sustainability alternatives. This is often due to gaps in education or limited exposure of global sustainability trends. Cultural resistance. Humans are naturally resistant to each organizations that have been using conventional methods for years. They have resisted adoption of new eco-friendly technologies or processes, especially if they disrupt existing workflows. Technological limitations. In certain fields, sustainable alternatives might not have matched the performance of traditional options. For example, biodegradable plastics may not have met all durability requirements of industrial packaging. Policy and regulatory gaps. In developing countries, sustainability regulations may be weak or poorly enforced. Without government pressures or incentives, companies may not feel compelled to go green. Lack of skilled professionals. Sustainable engineering often requires a cross-disciplinary knowledge combining mechanical, civil, environmental, and even more social sciences. The workforce shortage in this domain can limit implementation. At our college, we are overcoming these barriers through education and exposure, learning the tools, understanding the benefits, and preparing to advocate for change when enter the workforce. We don't just be engineers; we will be change makers who help companies overcome these obstacles. Case studies or examples. Let us talk about a few case studies that show sustainable engineering in action and how theory is being applied to solve real world problems. Pavagada Solar Park, Karnataka, covering over the 13,000 acres. This is one of the largest solar farms in Asia. It produces over 2000 milliwatts of clean energy and demonstrates how large scale renewable energy can be both economically and environmentally successful. It also provides environmental employment to local villagers. Tata Nano lightweight design. While the car may not have been commercial success, its designs focus on resource optimizations, fewer parts, reduce weight, and low fuel consumption. It was a case study in material efficiency and minimalism. Next, third is green buildings by Infosys. Infosys have built several LEED certified buildings across India. These offices use rainwater harvesting, solar panels, natural ventilation, and high efficiency lighting, reducing energy and water usage over 30%. Amul's dairy automation. Through improved cold chain logistics and efficient packaging, Amul ensures that milk is delivered with a minimal waste. Their community based model supports rural farmers in social educates emissions through optimized transport for environmental and increase profits economically. Tesla's battery recycling program. Tesla not only focus on electric vehicles but also recycles its lithium-ion batteries, closing the loop in a highly polluting industry. These examples inspire us that they show that sustainable engineering is not a luxury; it is scalable, impact, and the most important already happening. At our college, our goal should be to bring such innovation into every project we touch. So, I came to the conclusion now. To wrap it up, sustainable engineering is a future and in many ways. It already at the present, the world is undergoing a shift where climate, community, and capital are being reevaluated through the lens of a long-term responsibility. So let's recap what we have learned today. Sustainable engineering principles guide us to design some responsibly, efficiently, and longevity and minimal environmental harm. Life cycle things helps us look beyond the product's function to understand its impact from creation to disposal. Design tools empower us to measure, analyze, and optimize every choice we make. The triple bottom line ensures that our solutions are not only technically and financially should, but also socially and environmentally uh, available. We also saw that while there are barriers to sustainable engineering, they can also overcome with innovation, policy, and awareness. Finally, in the real world case studies remind us that sustainable solutions are possible, scalable, and already delivering values. At our college, Nita Meenakshi Institute of Technology, we are not just studying sustainability, we are preparing to lead it. Whether the work in the mechanical, civil, compute science, or computer science, or electric field, sustainability will interact with everything we do. So, thank you for being a wonderful audience. I hope this session has encouraged you to look at the engineering not just a technical job but as a social and environmental responsibility. Once again, I'm Yashwant MK at the Meenakshi Institute of Technology, and I believe that we are next generation of engineers have the tools, the training, and the passion of to shape the sustainable future. Thank you.